This is the free response question for the second part of the 1995 released AP exam on intermolecular forces. If you haven't done this question on your own yet, I highly recommend that you pause this video or ideally stop it and do the question yourself. Then come back and let's see where you could have gotten some points. Remember, you only need half of the points to be well on your way to a 3, 4, or 5. So with that being said, I'll take a short moment to allow you to stop, decide if you need to redo the question or rethink anything. All right, so coming across this diagram, the first time you open this test, you would see this diagram and go, oh, praise the Lord, it's an easy question. Because most of this is something you've seen in your pre-AP class or baby chem class. So we look at this as a phase diagram. Some people call them the martini diagrams because they look like a martini glass. I might even want to draw my little olive in there. Yes, more like an apple. But it's my martini diagram. So on the phase diagram, phase change diagram, there are a couple points we need to know. We need to know what V is, and you should hopefully learn that in baby chem. We need to know what W is, and hopefully you learn that in baby chem as well. And hopefully you know that every point along the lines are changes between states of matter. And it always goes solid, liquid, and then gas. Liquid goes in the martini. It's one way to remember it. So, thinking of all that, the minute I see this, the only other thing I might get from looking at this graph before I even read the question is I look at this as pressure, and they've highlighted a point of 1 atmosphere, which is standard pressure. It's what you usually are at. So I might get asked a question, what is this substance usually? Might be something good to think about. Okay, so what does point V represent? So point V is right here. What characteristics are specific to the system only at this point? So point V, hopefully you remember from baby chem class, is the triple point. And if each state of matter is represented on the graph, I should say G, that would be the point where the system has all 3 states of matter in equilibrium. Equilibrium is that buzzword, because each point along the graph, each line, is where the states of matter are in equilibrium. You're undergoing a phase change. So the point V is the triple point. The temperature and pressure are all 3 phases of matter are present in equilibrium. All right, that question's worth 2 possible points. It was 1 point for pointing out point V is the triple point, and 1 point for stating that all 3 phases of matter are in equilibrium. Again, that equilibrium is going to be our buzzword for this graph. All right, what does each point on the curve between V and W represent? So between V and W, oh, that is not what that line looks like. There we go. Between V and W, what does each point, each individual little spot on this graph, what does that represent? Yes, I realize I drew it and it looks like a pea pod. So what does it represent? Well, each point between V and W represents temperature and pressure where liquid and gas vapor gas, let's see, at room temperature, at normal pressure, we'll go with saying it's a solid. The vapor and gas exist at equilibrium. All right. This question again was worth 2 possible points. You got 1 point for pointing out that it's the temperature and pressure where liquids and gases represent, and that they are at equilibrium with one another. All right, letter C says, describe the changes that the system undergoes as temperature is slowly increased from points X to Y and then Y to Z. And I have no idea what my screen is doing. That was fun. Okay, so we got to break it down from X to Y and then Y to Z. 2 separate parts here. So, as heat is applied from point X to Y, the solid increases in temperature. Okay, what happens at Y? At Y, the solid goes from being a solid to a gas, so what do you call that? Sublimation. Vapor, or you can use the word gas, either one, into a vapor, and from point Y to Z, the vapor increases in temperature. Whew. So this question again is worth 2 points. 1 point for pointing out the change in solid state from solid into a vapor via sublimation. And 1 point for specifying that that happens specifically at point Y. Now, if you were at the prep session, or if you've been to a prep session, you may know the answer to D. But it's one of those things that as a teacher I have to apologize for. When we teach you phase diagrams, we usually do it for water. And it looks like this. Water is unique in the fact that when you cool water down, when it goes from being a solid, when it goes from being a liquid into a solid, water floats. However, with most phase diagrams for almost every other substance on Earth, it looks like this. Because most things, the solid form, that's sold, there we go, solid sinks. Because when you cool something down, the atoms get closer and closer together, intermolecular forces get stronger, and the density increases and therefore sinks. Water, because of the way the hydrogen bonds work, actually becomes less dense when you cool it, or when it freezes, not so much when you cool it, when it freezes, is less dense than its liquid state, so it floats. So the big difference here is that the slope of this line is positive, and it's one of the rare ones that does that. Most of the time, the slope of this line is negative. So if you have a positive slope on a phase diagram between solids and liquids, the solid is less dense than the liquid. If you have a negative slope, the solid is more dense than the liquid. So let's go back up to our graph, if I can. There we go. Would this be a positive or negative slope? Well, this would be a positive slope. So, wow, I'm really in backwards. This is a negative slope. There you go. This is the positive. Well, that's a positive slope. So that means that the solid is going to sink. The solid will sink because the slope of the line between solid and liquid is positive. And it's one of those things you just had to know. So your teacher had to just correct themselves after teaching it to you a particular way in baby chem. I apologize if this is the first time you've seen it. We don't mean to be mean. It's just this is the most common phase diagram around because it's easy to chart and see and looks very nice. Kind of looks like a butt, but that's not important. Most substances, though, look more like this, with a positive slope for the difference, or for between solids and liquids, and this is because the solid sinks, or the solid sinks because of